Hello everyone, this is Dr. Swapnil. I am starting this particular channel to help my students as well as those who are in need of a help for organic chemistry. Specifically, those who are struggling with Augur 1, Augur 2, or sometimes some students, those who are preparing for ACS organic chemistry exams. They generally come across similar these kind of problems, which I'm sharing with you on screen. So in this particular channel, I will be taking different problems, the sample problems, which a few of my students have already discussed, and they shared with me those problems. So the common problems, which I'll be discussing uh, throughout the different videos on this particular channel. So if you have any questions, if you would like to have more information on this, please let me know. I'll try to help you in the comment section. Okay, here the particular question is asking cycloserine is an antibiotic isolated from microbes. It is used in conjunction with other drugs for the treatment of tuberculosis. Of course, this question is asking for many different questions further. What is the molecular formula of a compound? How many sp3 hybridized carbon atoms are there? And sp2, and so on and so forth. So let's give all the answers or work on all the answers one by one. Typically, A here, question A is asking what is the molecular formula of this compound. Now, this molecular formula, this particular structure is shown with a bound line structure, or sometimes some people call it as an line angle structure. Here, each corner is a carbon, and carbon is expected to form four bonds. So, whichever carbons that's not showing four bonds, that means the rest of the bonds are expected to be with a hydrogen. Take an example of this particular carbon over here. You can see this carbon is shown with one, two, and three bonds. So the fourth bond is expected to be with hydrogen. Go for this one. This carbon is shown one bond with the oxygen, another bond with the first carbon, and then the rest of the two bonds are not shown. So we expect that to be, or we assume that to be a CH bond. So rest of the two bonds are with CH2. So this is CH2 group. This is a CH group. The rest it is nitrogen, hydrogen, and oxygen. So this carbon is attached to the oxygen with the double bond, and rest it is visible pretty much. Okay, so to find the molecular formula, let's count for number of carbons here. So one, two, three. There are three carbons, so C3. Then comes hydrogens. So we got one hydrogen here, two hydrogens here, so total three, four, and a five, and six. Total six hydrogens. Nitrogens, if you see, one, two. There are two nitrogens. Then comes two oxygens as well, O2. And this would be the molecular formula of that particular compound. Let's take next question. How many sp3 hybridized carbon atoms are presented in this particular structure? Okay. sp2 hybridized carbon must not form a pi bond or in the form of it like a double bond or a triple bond. So any carbon that's forming only single bonds with the different atoms, it will be sp3 hybridized. So here, this particular carbon is forming all single four bonds. This carbon is also forming all single four bonds. So that's why there are two sp3 hybridized carbons. However, this particular carbon is forming one pi bond with oxygen in a double bond, and that's why this would be sp2 hybridized, not sp3. They're specifically looking for carbons, so we are focusing on carbons only. Nitrogen and oxygen is out of the question there. So let's write down sp3 carbons. Number of sp3 hybridized carbons is 2 in this case. See, if you look at the carbons here, we have 3 carbons. Out of those 2 are sp3. The third one is forming a pi bond in a double bond. That's why this particular carbon is expected to be sp2 hybridized carbon. So we can simply say the number of sp2 hybridized carbons is 1. There is no triple bonded carbon, and that's why no sp hybridized carbon. When a carbon is forming 2 pi bonds and one single bond, one sigma bond with another carbon or another nitrogen or other atoms, then in that case, that particular carbon is expected to be sp hybridized carbon. However, there is one kind of an exception to this rule. When central carbon is present in an allene, then in that case, it can be sp hybridized. So allene is a separate case, so we'll talk about allene in, as we discuss a lot many different kinds of problems. Maybe we will come across, and then we can try to work on those. Okay, I'll discuss with sp hybridized carbons in case of allene in a separate case. So here, as there is no triple bonded carbon, no allene carbon, so that's why it is there is no sp hybridized carbon. So number of sp hybridized carbons is 0. Next question is, how many lone pairs are present in this particular structure? Okay. Oxygen can have 2 lone pairs because it's forming 2 bonds, so that's why it will have 2 lone pairs. Remember, oxygen contains total uh, uh, total total 2 lone pairs, and its valency electrons is number of valence electrons is 6. So out of 6, 2 electrons are utilized to form 2 bonds with other atom, and rest of the 2 are utilized as a lone pair. Nitrogen, on the other hand, it will have, if it is forming 3 bonds, it could be pi bond, it could be sigma bonds, single bonds, it doesn't matter. If it is forming 3 bonds, that means it will have 1 lone pair, because nitrogen, being from a 5th group in the periodic table, it has 5 valence electrons. Out of those, 3 are utilized to form sigma bonds, or 3 are utilized to form bonds with the other atom, and rest of the 2 are utilized to as a lone pair on that atom. So unless and until nitrogen is forming 4 bonds, we can consider nitrogen to have 1 single lone pair of electrons. They are specifically asking for lone pair of electrons, so 2 on this oxygen. So let me draw the 2 electrons on oxygen. So there are 2 lone pairs on this particular oxygen. Then this oxygen will also have 2 lone pairs, because yes, there will be a case when oxygen is forming total 3 bonds. Then in that case, it could have only 1 lone pair, such in a case of a hydronium ion, H3O plus. So that would have only 1 lone pair. Okay. Then nitrogens, as I said, will have 2 lone pairs. Sorry, 1 lone pair each, so total 2 nitrogens, so 2 lone pairs on 2 different nitrogens. Okay. So total number of lone pairs, we have 1, 2, 3, 4, 5, 6. There are total 6 lone pairs on these. Present in this particular structure. So total number of lone pairs is 6. Make sense? Okay. Now let's go for F. Identify each lone pair as localized or delocalized. Localized lone pairs are not involved in resonance, whereas delocalized lone pairs are involved in resonance. Only lone pairs on one of the nitrogen atom is delocalized via resonance because it is next to the pi bond. The other lone pairs are all localized one. So I can simply show that this particular oxygen lone pair is localized. Same goes with this nitrogen because it's not in conjugation with this pi bond, so it's also localized. This oxygen lone pairs are also localized one. But the lone pair on this nitrogen particularly is delocalized. So I can simply say this is delocalized because we can simply draw a resonance structure by moving these pi electrons across the pi bonds here. So the lone pair on a nitrogen can be delocalized over this pi bond and the oxygen. So that's why this lone pair is expected to be delocalized. Rest of the lone pairs are pretty much localized. Okay, so we can simply say that there are three localized lone pairs. So number of two and number of delocalized lone pairs is only one. They're not delocalized. Is only one. Next, they're asking for identify the geometry of each atom except the hydrogen atoms. Of course, hydrogens will have only it can form only one single bond, so that's why we don't need to worry about the hydrogens. But rest of the atoms, let's look at this. As this nitrogen is not forming any pi bond, that means it's a sp3 hybridized. And as this is sp3 hybridized, it will have trigonal pyramidal geometry at nitrogen. Okay? So what I'll do, I'll take the structure again and then I'll try to write all the geometries of different atoms. So let's take this over here. This nitrogen is expected to be trigonal pyramidal. sp3 hybridized nitrogen will have trigonal pyramidal geometry. The bond geometry I'm talking about. Electron geometry, on the other hand, will be tetrahedral. So this is molecular geometry I'm talking about. So trigonal pyramidal. If it has four bonds, if nitrogen has four bonds, then in that case we could say that nitrogen would have the tetrahedral geometry, molecular geometry. But now we have only a bonded pair of electrons in the nitrogen and one lone pair. That means it's a trigonal pyramidal geometry. This carbon is sp3 hybridized. sp3 hybridized carbon will always have a tetrahedral geometry. This carbon will always have a tetrahedral geometry because it's a sp3 hybridized. So tetrahedral. Next, CH2 carbon. Of course, as expected, it is also sp3 hybridized, and that's why this will also be a tetrahedral geometry. Oxygen, on this case, it's sp3 hybridized oxygen, and there are two lone pairs on it, two bonded pair of electrons there. So that's why it is expected to have a bent geometry, bent molecular geometry. So this would be a bent geometry. It is something similar to that of the water molecule, where oxygen, central oxygen atom, is having two bonded pair of electrons and two lone pairs. So that's why bent molecular geometry. If you talk about the electron geometry of this oxygen, then in that case, that would be simply tetrahedral geometry because this is sp3 hybridized nitrogen. The nitrogen, this is quite important here. Although the nitrogen is in resonance, or lone pair on a nitrogen is in resonance with a pi bond here on a C double bond O. However, this nitrogen is expected to be sp3 hybridized. Yes, if you consider those to be sp2 hybridized, then in that case, that would be trigonal planar geometry. Now, if you consider this to be sp3 hybridized, then in that case, you cannot delocalize this lone pair of electron on the pi bond. But we know, we already discussed that the nitrogen lone pair is expected to be delocalized over a pi bond. That means to make this lone pair delocalized in a resonance, the nitrogen needs to be sp2 hybridized. As this nitrogen is sp2 hybridized, it will be a trigonal planar geometry. Remember, this nitrogen lone pair is not in a conjugation, so that's why this is a trigonal pyramidal geometry. But this nitrogen lone pair is in a conjugation via resonance, so that's why this nitrogen will have a trigonal planar geometry. It's a trigonal planar geometry. This particular carbon, you would expect, as it is sp2 hybridized, so it will also be a trigonal planar geometry. So it will also be a trigonal planar geometry. sp2 hybridized carbon will always have trigonal planar geometry. What about this oxygen? Oxygen here is, I would say it is not much relevant because it's only connected to one atom. So the geometry here would not be that important. But sp2 hybridized oxygen would be expected to have a trigonal planar geometry on them. But don't worry about that. There is no point in discussing the geometry of this particular oxygen because it's forming only one, or it's bonding with only one atom. Okay. We're done with the G. Draw. Next question is draw all significant resonance structures of this particular molecule. Okay. So we begin by looking for the phi patterns, focusing first on any patterns that employ just one curved arrow. In this case, there is another pattern that requires two curved arrows as well. But we'll start with just a pattern using just only one curve. Okay. So when you're drawing a resonance structure, let me draw the first molecule with a single pi bond delocalization. So I can move these pi electrons onto the oxygen to create a positive charge here and negative charge here. So that will be a first resonance structure. Then comes the second resonance structure, where, so this is the first resonance structure. Resonance structures should be shown with this particular arrow, a double arrow arrow. So the positive charge on this oxygen and negative charge on positive charge on a carbon and negative charge on oxygen. Now, the lone pair on a nitrogen can be moved on to the between the carbon and positively charged carbon and nitrogen, adjacent bonds. So this will be another resonance structure further. So there are total 3 resonance structure you can draw with this particular molecule. Okay, whenever we are drawing these resonance structure, we generally draw it with like these arrows, and we often draw them in square brackets. Okay, so the square brackets indicate these are the resonance structures of each other. Now, one may ask for me further question that which one is the most stable? As per the rules governing resonance structures, the first structure which does not have a charge separation at all, that's why this would be the most stable resonance structure. It's a neutral structure, so it's more stable resonance structure. The third structure, where the charge separation is better, far away from each other as compared to the second one, that's why this would be the second structure with a stabilization function. And this one would be the least stable. So more stable, intermediately stable, and least stable structures as given here. Okay, so we have completed this particular question. Now, at the end, I would like you, if you like my teaching style, if you like my discussions, kindly just go through my profile on the given link. Please go through those, and if you'd like to learn more in details along with me online, please join me through by booking the lessons there. Okay, thank you so much. I'll see you in the next lesson. Bye bye.